I'm going to do two more examples of looking at sequences and their limits. Let's look at a sequence, say the arctangent of n to the n. So this is a common thing where we've got one function inside of another. In other words, it's a composition. And so we're asking, does the limit as n goes to infinity of this sequence, does this exist? And if so, what is it? And the key is when you're looking at compositions, look at what the inner function does. This is going to be about the limit of what the outer function does when the inner function does whatever it's going to do. So let's just break it out. Does the inner limit exist? Well, it doesn't exist as a number, but it certainly does something very predictable. It goes to infinity. This goes to infinity quite quickly. 2 to the 2, 3 to the 3, 4 to the 4, 5 to the 5. This grows without bound. And so often you think of this as a bad idea, a bad thing. But this is actually great because it says that we're just really looking at the limit of arctan when its argument gets really, really big. And that's the usual notion of taking a limit. It's just getting there faster. So this is going to be equal to, if the arctan cooperates, the limit as, and it's often good to use a different variable. It's really a substitution process. Let's say m goes to infinity of arctan m. And really, we could say we're just denoting m as an abbreviation for n to the n, and the key thing is we know that m really is going to infinity. So this is getting a little close to manipulating infinity as a number, but it's not really. It's just saying that as n goes to infinity, as n increases without bound, this quantity, which we're now denoting m, increases without bound. And this question asks what happens to the arctangent when its argument increases without bound. Well, that's a known thing. Again, that's the limit. One more change of variable, or change of concept here. X goes to infinity, a real variable of arctan x. And that's our standard strategy from the previous video of if we know the graph, if we know this function and its limit as a function of a real variable, then we're good. And that's pi over 2, because it's a well-known fact that the graph of this thing looks like this with an asymptote at height pi over 2. So this thing totally works. So that's a good strategy of analyzing something from the inside out if it's a composition of functions. And if you know what the inside does, then you know, and then you can plug it into the outside. Sometimes this limit will be finite, and then it's just what happens when you just plug that number into this function. But this is a little more interesting case. So one last example for this batch. Let's do something that's really pretty complicated. Let's modify that previous example. Just that same one. And then let's add some stuff to it that makes it a little more wacky. Okay. If you graph these, I'm not going to graph it carefully. What's going to happen here is you've got these arctan values, and then at the start, these are pretty wild. This goes plus or minus, plus minus, plus minus. And at the start, n cubed grows pretty quickly, and factorial takes a while to catch up. So roughly, you might have something that's kind of wiggling around a bit, but then what you notice is that it actually heads down near pi over 2 again. So in other words, I claim the evidence shows that the limit of this thing is, again, just exactly pi over 2. So let's show that more carefully. Well, first thing is the limit of a sum is the sum of the limits, as long as both of them exist. Well, this one does exist. And then if we can show this one exists as a finite number, then we're going to be good. So you can write this out and start out with this process, as long as you know that if you get a DNE for either one, then you have to start over. And I've got some interesting glare here. I'll try to kill that. So that's one of the things we want to illustrate here, is just breaking things into pieces. Okay, so we already know this guy, pi over 2 plus. Now what about this one? Okay, Well, let's do an informal treatment first. When n gets big, n cubed definitely gets big, but 10 cubed is 1,000. But 10 factorial is 10 times 9 times 8 times 7 times, that's much bigger. And 100 cubed is not even close. 100 cubed is 1,000,000. 100 factorial is really big. It's like 10 to the 70th or something like that. Okay, so and then the minus 1 to the n, what is that going to do? When these numbers are really, really small, when this quotient is really, really small, it makes it wiggle a little bit, but it wiggles closer and closer and closer to 0. So that should be fine. So um, I'm going to put a 0 question mark just to say we expect that to be 0. So we're really just trying to show that this limit is going to be 0. So let me show you just a couple ways of doing that using some of the theorems. First of all, there's this theorem that says that if I want to show a limit goes to 0 and it has some weird signs, the signs don't really matter. So let's say, if I can show the limit of n cubed over n factorial equals 0, well, since that's the absolute value of this guy, n factorial, that will show that the limit with the sign included goes to 0. And it's going to be a very important thing for us to look at the special case of showing that limits are actually 0, not just that they exist, but that they're equal to 0. Okay. All right, so that deals with the sign issue, but we still need to show this a little carefully. Okay. I'm just going to go ahead and give myself some more room up here. Okay, and so now we just need to look, let's see, n cubed over n factorial. Let's break that out a little bit. That's n times n minus 1 times n minus 2. Notice, as soon as I've written that down, when n is really big, the n minus 1, minus 2 don't matter. This should be really close to 1. That's very well known about what it is. And so I'm just going to stop and then just say the rest of it is n minus 3 factorial. Using a really nice property of factorials, and it's basically the recursive definition of factorials, that any factorial is the biggest number times the second biggest, third biggest, times all the rest of them, and you can package those up very conveniently. Okay, so that suggests, hey, what if I take the limit as n goes to infinity of this guy? Again, as long as I can show both limits individually exist, that's a product of this one times this one. Aha, now we're good. That's a 2, by the way. This is one of those ones that's the same as if it were the limit as x goes to infinity, and we know how to deal with that. Multiply by 1 over n cubed, top and bottom, and it all goes to 1. This clearly goes to 0 because this is growing very quickly, and so this is going to 0. So this whole thing is 0. Aha, we have shown that. So the wiggly signs don't really matter at all. Instead of just coming down to 0 in one direction, it wiggles to 0, but who cares? That's equal to 0. And so I can take off that question mark. And yes, both of those individual limits in the sum originally existed. And the final thing is just the pi over 2 we had before. Okay, that's what I want to do today.